My name is Neil Heckman, and I'm with the chemistry department, and I have the privilege today to introducing our faculty invited lecturer for spring 2026, Dr. Brad Dinardo. Brad Brad is originally from Pennsylvania, where he earned a bachelor's degree from Juniata College. After his undergraduate degree, he moved to the University of Colorado, where he earned a PhD in physics, and then joined the faculty here in 2019. He's currently an associate professor of physics at Hastings College. Let us give a warm welcome to Dr. Brad Dinardo.
Thank you. I appreciate everybody coming out. So, I believe the most influential invention ever made is the laser. The importance of the laser to science and technology and our everyday lives is immeasurable. So, does anyone here know who thought up of the laser? Da Vinci? I mean, he may have. Everyone in here knows who thought up of the laser. It was Einstein. So in 1916, Einstein wrote a paper, and in this paper, which is in German, I got some translations. Oops. Einstein said that he predicted that a single wave of light can stimulate atoms in a material to emit a cascade of more and more waves of light. And this stream of light will travel in the same direction with the same energy as the original wave of light, right? So this kind of sounds like a laser, right? We have light coming out of something, right? But it was 1916. They didn't have the technology at the time, and in fact, it would take quite some time until we had the resources to take Einstein's idea and turn it into reality. So in 1958, Charles Towns here, which we can see in the picture, he and his colleague Art Shallow produced the first microwave laser. So this is called the maser. So think of a laser pointer, but instead of a red beam, it fires microwaves. And this achieves Einstein's 1916 prediction, but for microwaves, not for visible light. So it's not quite a laser, but you can think of this as the predecessor of the laser. And it is really cool. He did win the 1964 Nobel Prize in Physics for this. So it was a big accomplishment in science. So it would be about 2 years later when the first laser was actually developed. So this is Theodore Maiman. He's the person who produced the first laser beam, and he did it in a ruby crystal. So basically, there's this little crystal of ruby here, and by using a high voltage power source, Theodore Maiman was able to stimulate this ruby crystal to produce a red beam of laser light. And so you'll hear this is called the ruby laser. This is what it looked like. This little container here is where the ruby crystal is. So this is actually in the Smithsonian Museum in Washington, D.C. So you can think of this as really the first laser. And I wanted to show this, right? This is kind of blurry, so you really can't read this, but I wanted to show this here is the entire publication that Maiman wrote announcing the laser, right? This is less than 300 words, right? This never happens. So he basically just said, yeah, we did it. So Maiman makes the first laser, and it's also around this time that the acronym laser was coined. So laser actually is an acronym, and laser stands for light amplification by the stimulated emission of radiation. And all 5 of these characteristics are what make a laser a laser. They're what differentiates laser light from the light from a light bulb or the light from a sun. So laser light is very specific. So I want to address each of these 5 characteristics to see, what makes a laser a laser. So the first is the light, the laser light. Laser light is monochromatic. Mono, one. Chromatic, meaning color. So laser light is one color. And laser light is also collimated. What that means is it's a nice focused beam. It's not expanding outward in space as it propagates. Additionally, the light is what's called coherent. And this is really the big one for the laser. Look at how the light waves are all oscillating together in unison, right? That means a coherent beam of light. All the light waves oscillating together in unison. Something that's incoherent would be like this, right? It's not waving in unison, and it almost looks like the waves are coming out randomly, right? That is incoherent. So laser light is coherent. If we look at sunlight, sunlight puts out lots of different colors, and they're not all waving together in unison, so that's incoherent light. An incandescent light bulb also puts out light sort of randomly, so that's not coherent, right? So I hope you can see here how the light from the sun, the light from a light bulb, is very different from the light from a laser. Right, where here we have this nice unison, everything oscillating together. So the light is coherent. So that about covers the light. The rest of these words here, right, if we're going to understand the rest, we have to look at the energy structure of the atom. Okay, so here's your basic picture of the atom. You have the positive nucleus here. You have the negative electron orbiting it there. And atoms can have different energies. So the lowest energy the atom has is called the ground state. That happens when the electron, as it orbits the nucleus, is in the lowest possible orbital radius. You could think about it, it's orbiting as close as it can, as close as it's allowed to the nucleus. So that's the lowest energy state. We call that the ground state. So when atoms are in a higher energy state, their electrons orbit further away from the nucleus. We call these an excited state. So a higher energy level, higher energy is called an excited state. And the key thing here is the electron is orbiting at a larger orbital radius. So basically, you can think about it as there are really 2 types of energy levels for atoms. The ground state, small orbital radius. The excited state, big orbital radius, okay? Now, where do you think atoms naturally exist? They exist in the ground state naturally. So if you're going to get atoms to be in the excited state, you have to give them energy, right? You have to do something to give them energy. Otherwise, they're going to exist in the ground state. So suppose we have an atom that's in the excited state, right? Maybe we shocked it with electricity and put it in this excited state. The atoms only stay in the excited state for a few nanoseconds. It's very short. And what happens is they rapidly de-excite and go back to the ground state. And here's the key, when that happens, the atom emits fluorescent light, okay? And this happens spontaneously. So we call this process spontaneous emission, right? It spontaneously emits light. Now, different atoms have different orbital structures, so you can get lots of different colors when you have this spontaneous emission, right? The orbital structure of hydrogen is different than helium, which is different from neon, different from argon, right? So you get different colors depending on what atom you're using, okay? This is spontaneous emission. An excited state atom spontaneously goes back to the ground state and emits some light. Okay, but if you do remember, the SE in laser was stimulated emission, not spontaneous emission. Okay? So here is where Einstein's 1916 theory is going to come in. All right, let's see if we can follow this. So, if fluorescent light emitted from one atom strikes another atom that is still excited, meaning it hasn't spontaneously decayed, it's still excited. So if this spontaneous emitted light strikes an atom that is still excited, it can stimulate this atom to release its fluorescence early, right? It stimulates it to emit the light. So it happens early, before it can spontaneously de-excite. So since the light that's emitted from the excited atom is stimulated rather than spontaneously emitting, we call this process stimulated emission. And what's interesting is the light that's generated via this stimulated emission oscillates in unison with the original stimulating light wave. This is what Einstein was talking about back in 1916. So he's the one who predicted this. Okay, so that's how you can have stimulated emission. But suppose that this stimulated emission encounters more excited atoms. So, for example, here's maybe light from an atom that's being emitted, and it encounters an excited atom, and there's stimulated emission. So now I have two waves of light. Now suppose these two waves of light hit another excited atom, and that stimulates some fluorescence. Now I have three waves of light. And now these three waves of light encounter an excited state atom and get more stimulated emission. Now I have four waves of light. We're getting this sort of chain reaction here. We are amplifying the light. This is light amplification by the stimulated emission of radiation. This is a laser. Now, what we want to do is, let's put this, our atoms here inside of a cavity. You can think of that as like a box. So put this, put these atoms inside a box, and we're going to have a special box that has mirrors on the two ends. On the left side here, I have a mirror that is 100% reflective. And on the right side here, I have a mirror that is 99% reflective. So that means that as this light is being created via stimulated emission, when it encounters this mirror, roughly 1% of it is going to escape. The rest is going to reflect back, and then it keeps, going back and forth. And so what we'll get is a little bit of light will escape here. So let's sort of put all of this together to make a real laser. So the genesis of the laser light is you have to have a pump mechanism, right? You have to initially excite the atoms. So usually we use electricity to pump atoms into their excited state so we can start the laser process. That electricity could come from a battery if you have a little laser pointer. It could come from a wall outlet if you have a more intense laser. But the bottom line is we use electricity to pump atoms up into their excited states. What happens next is you get spontaneous emission. Right? Within nanoseconds, some of these excited state atoms are going to de-excite and emit laser light. And now that light is going to stimulate other excited atoms to emit fluorescence themselves. So we start to get fluorescence that's generated, and again, a little bit is going to escape because this side here has it's a 99% reflective mirror. So we're stimulating the atoms to emit light. Small amount is escaping through this partial mirror. And imagine this process is going to continue as long as I keep my electrical source on, right? As long as I have my power on, that's going to keep atoms to be re-excited. So this just continues, right? It continues. We get more excited state atoms that stimulate, their stimulated emission, light is generated, so you start to build up more coherent light inside. Notice how this is all oscillating together in unison. We get more light that escapes through this partial mirror, right? And all of this is oscillating in unison. And as long as I keep my electricity on, as soon as these atoms de-excite, they get re-excited and stimulated again. And this process just continues back and forth, and the laser inside quickly reaches an equilibrium. You have atoms excited, then they de-excite, then they excite, then they de-excite. All the time they're giving off fluorescent light that all is oscillating together in unison, and a large amount of monochromatic coherent light builds up inside, and of course roughly 1% of that is allowed to escape, and we have a nice laser beam that is emitted and ready to use. Okay, so I kind of want to summarize everything I just said with an animation. This is a really cool animation. I did not do this animation, but this is just too good to not have here. So what I'm about to show is basically what I just showed here from start to finish as to how we can generate laser light. And I should mention that before we do this, any idea of how many times this excite, de-excite is happening per second inside this laser? I mean, it's a few billion times. So imagine what I'm about to show, it's happening a few billion times every second. Okay, so here's our atom, and it's in the ground state. Here's an excited state atom, higher radius. Now here comes some light, and it's going to cause stimulated emission. De-excites, and it gives off some laser light. They travel together in unison. Now put lots of atoms like this in this box with mirrors, and we have stimulated emission, and stimulated emission, and stimulated emission, stimulated emission, stimulated emission, more stimulated emission, and look what we have building up inside. Lots of light waves, all oscillating together in unison. And we allow a little bit to come out, and there's your laser beam. Okay, so these are some credits from whoever made this, right? That's a wonderful animation. Okay, so the atoms that you're using inside the laser, right, you can use different atoms. So that's how you can get different colors, right? So you could use helium neon atoms, you could use sodium atoms, you could use CO2 molecules. So different types of atoms and molecules in our laser produces different laser light, right? So that's how you can get reds and yellows and blues and, you know, purples, right? So we can get different lasers with different colors. Now, we use lasers and rely on them every day, right? Things like the internet, right? This is the picture of the internet, right? The internet uses lasers. We use lasers for medical technology. We use lasers for fabrication of computer chips. We use lasers for cell phones and navigation. Barcode readers, right? I mean, how many times do we use those? There's lots of science applications to probe the atom and understand the atom, right? And so this is why I said the laser is the most influential invention. So Einstein thought of it in 1916. It was, you know, it took till 1960 to actually make it. Could you imagine if we could have somehow, you know, shrunk this gap, how much further ahead technologically we would be today, right? I mean, you can't even conceptualize how far ahead we would be today. So there are so many applications that we use in science and technology and amenities from the laser. Now, my interest in lasers is actually using them to make things cold. So some of you might be thinking, lasers making things cold? Well, wait a minute. We've seen pictures of lasers cutting through metal, right? Or burning through something, right? How can lasers possibly make things cold? Well, this is a puzzle that we're going to have to solve today. But if we're going to talk about temperature and cold, we need to first define a temperature scale. So the United States uses the Fahrenheit scale. So the Fahrenheit scale is defined by saying the following. We're going to say, okay, we're going to call arbitrarily the boiling point of water 212 degrees Fahrenheit, and I'm going to arbitrarily call the freezing point of water 32 degrees Fahrenheit, and then just make tick marks in between there, and you have your scale, right? It's kind of arbitrary, right? But that's how the Fahrenheit scale is developed. The lowest point happens to be minus 459 degrees Fahrenheit, and you have the Fahrenheit scale. Right, this is what most of the United States uses. The rest of the world uses Celsius for the most part. But this isn't really any better when you talk about arbitrariness, because they do the same thing. They just say that the boiling point of water is 100, the freezing point is 0, so at least it's nicer numbers. But it's still kind of arbitrarily defined. And the lowest point of the Celsius scale is minus 273 degrees Celsius. So there's nothing special about water. These aren't really great scales to use for science. Science uses the Kelvin scale. And so just for reference, the boiling point of water in Kelvin is 373 Kelvin. The freezing point of water is 273 Kelvin. But the big feature of the Kelvin scale is where it's defined from, and it's defined from 0, right? This is 0, so this is absolute 0. 0 Kelvin, right? 0 Kelvin is 0, where 0 Celsius and 0 Fahrenheit are not truly 0. So the lowest temperature on the Kelvin scale is absolute 0. That's the lowest possible temperature we can have, and that is where thermal energy is 0. Something else that's worth mentioning is thermometers that we see here are also speedometers, because higher temperature atoms and molecules move at a faster speed. So if you look here, we have warmer atoms. They're moving faster than cooler atoms, right? That's because the warmer atoms, they're at a higher temperature. They have more thermal energy, so they move faster. Cooler atoms, right, at a lower temperature have less energy, and so they move slower. So if you think about it, thermometers really are speedometers. The lower temperature you have, the slower your molecules and atoms are moving. The higher temperature you have, the faster they're moving. So in this room, we're at room temperature, right? Maybe it's like 70 degrees Fahrenheit, 300 Kelvin. Does anyone have any idea as to how fast the molecules in this room are moving, give or take? Any guesses? 200 meters per second? It's around 1,000 miles per hour. It's very fast, so it's faster than an airplane. And so just as a sort of reference point, the molecules in this room are around 1,000 miles per hour. So here's a question. Why might we want cold atoms, right? What would be the benefit of having cold atoms? Right, any ideas? Oh, they stay still because, right, they would be easier to maybe use or easier to observe, or I could do something with them, right? I can't do something with them if they're moving around at 1,000 miles per hour, but if they're really cold, perhaps I could, hold them here, right, and do something with them. And that's exactly right. So I want to give two examples of that emphasize this. And the first is with a clock, or what's called an atomic clock. So if you're going to make a clock, what you need is something that ticks regularly, right? So we see this clock, right? The pendulum is just going back and forth regularly, tick, tick, and you use that repetitive motion to tell time. So atomic clocks use atoms to tell time. So here's, an atom, and the outer electrons in the atom can vibrate back and forth with an incredibly precise frequency. So you can think of this vibration as a tick, and it's very, very precise. In fact, we know, for example, if you take cesium, which is just an atom on the periodic table, we know that the outer electron in cesium vibrates in 1 second this exact amount of time. 9,192,631,770 times exactly in 1 second. And so this ticking is going to help us keep time more accurately than any kind of mechanical clock. So here's the idea of how to make an atomic clock. You need to observe the cesium atoms vibrating. And you say the following: I'm going to count how long it takes this atom to vibrate back and forth exactly 9,192,631,770 times. I count how long that takes. And when I count how long it takes, you get exactly 1 second. And in fact, this is a little misleading. There are zeros here out to 9 zeros. We know it exactly out to 9 zeros that it takes 1 second for the atom to vibrate this many times. So I have to observe that. Now this is what an atomic clock looks like. The atoms are inside this chamber here, and this is where they observe the atoms vibrating back and forth. Now imagine if the atoms were flying back and forth at 1,000 miles per hour. I can't measure this, right? I need them to be moving slowly. If they're not moving slowly, I can't count how long it takes for them to vibrate. So you have to cool the atoms down to a low enough temperature that I can actually observe them and take some measurements and use that to build a clock. Okay, another sort of example of this is with a quantum computer. So this is a really cool picture. This is a 16 by 16 grid of individual atoms, and they're all confined in place, right? Every one of these dots that you see here is one atom. And so what you can do to make a computer is you take neighboring atoms and they can link up and they can talk to one another. They can interact with one another. And you can make them work together to act like bits of ones and zeros, right? And they can work like a computer. The point here, though, is these atoms are right here, right? I can see them, right? If they're flying around at 1,000 miles per hour, I'm not going to be able to hold them in place and do something with them. So if I'm going to build a computer here with these atoms, they have to be cold enough that, I can do something with them, right? They're not flying around at 1,000 miles per hour. So why do we really want cold atoms? What's the benefit? Well, if I'm going to observe atoms or do something with them, they can't be moving and zooming around the room at 1,000 miles per hour. They need to be moving slow. They have to be cold. Okay, so as an experimentalist, I then ask, well, how cold do they have to be, right? What would be the best possible scenario? Absolute zero, right? If they're absolute zero, they would be at rest, right? So they would be at rest, and I could just observe them in place, right? This would definitely be the best case. Their speed is zero, no motion, no thermal energy. So here's my question. Can we get to absolute zero? How close can we get to absolute zero? Is it even possible to get to absolute zero? Well, we got to get to 0 Kelvin. So let's think of some things that are bitterly cold. How about the Nebraska weather, the winter weather in Nebraska, right? So I looked this up, and this is according to Google. This is the lowest temperature ever officially recorded in Hastings, Nebraska. So this is minus 34 degrees Fahrenheit. So this is not like the wind chill, this is the raw temperature. And minus 34 degrees Fahrenheit is 236 Kelvin. And at that temperature, the speed of the molecules are around 995 miles per hour. So this harsh Nebraska winter weather is really, really cold to us, but this is way above absolute zero, right? 236 Kelvin. So we're going to have to get colder than this. How about the coldest temperature ever recorded on Earth? So this is the Vostok Station in Antarctica. This was recorded sometime in the 80s, an official temperature of minus 129 degrees Fahrenheit. So very, very cold. Average speed of the air molecules, still pretty high, 877 miles per hour. 183.5 Kelvin, right? We still have a lot to go to get to absolute zero. So we need to get much colder than this. So what is something else you know that is really cold, right? That might be in the labs here. I heard someone say liquid nitrogen. Liquid nitrogen, right? Right, we have that. So liquid nitrogen, minus 321 degrees Fahrenheit, right? We're getting very, very cold. 77 Kelvin. This is very cold, but we're still quite above absolute zero. Right, so we're going to have to crank it up a notch, right? We need to get really cold. So helium is the gas that fills your party balloons, and you can cool helium, and it eventually will liquefy. And liquid helium is a bone-chilling minus 452 degrees Fahrenheit. That's 4.2 Kelvin. Okay, we're down to single digits. The average speed of the molecule is still 130 miles per hour. But think about this, if I have liquid helium, perhaps I can keep cooling the liquid helium and get even colder. And that's exactly what we can do. So if you've heard of like cryogenics, we have what's called a dilution refrigerator. So this is this beefy refrigerator here, and this is the inside of it, right? This looks like something from some mad scientist's laboratory. But you can use this sort of refrigerator on steroids to cool the liquid helium to 10 millikelvin. That's 0.01 Kelvin. So this is so cold that Fahrenheit and Celsius really don't matter anymore, right? So we're just going to look at Kelvin. And the average speed of the molecules are 16 miles per hour. So this is about as cold as you can get with any kind of refrigeration, right? I think we would all agree this is really, really cold. This is about 30,000 times colder than the air in this room right now. But we can go colder. We can go much colder than this. To get even colder, we have to use lasers. So the problem though is, right, we have to go back to my original question, how can lasers make things cold, right? It's lighting the match on fire. How can I make something cold? Right, get a laser right now, right? If I beam it on my hand, right? If you beam a laser on your hand, do you feel cold or would you feel heat? Right? You feel heat, right? You don't feel cold. But here's the trick. Atoms by themselves, right, such as, a collection in a gas, by themselves are different. So here's what I want to do. I want to take some laser beams and have them shine on a collection of atoms right here. right? So think of 6 different laser beams all, aimed at, a gas of atoms. Now here's where atoms in a gas are different. When atoms absorb laser light, they have no other choice but to re-emit the light in the form of fluorescence. So what happens is I shine lasers and fluorescence, comes out. The light this fluorescence is emitted from the atoms here. So think about this. We have light in, light out, right? The energy that is emitted from the atoms is equal to the energy that is absorbed by the atoms. So here's a question. In this setup, if energy emitted equals energy absorbed, how does the atom's energy change when it absorbs laser light and emits laser light? How would its energy change? If energy emitted equals energy absorbed, it doesn't change, right? There's no change in energy. So in this setup, every time I hit a laser beam on atoms, it absorbs that light and just re-emits light. Energy in equals energy out, and nothing changes. Everything remains the same. But, right, we're scientists. What if we could exploit something? What if we could create a very small difference? What if we could somehow make a situation where the energy that is emitted, right, from the light that's emitted, is a little more energetic than the energy of the light that is absorbed? Well, what's going to happen there? Right? What's going to be the net effect? If the atom emits more energy than it absorbs, overall, it's going to lose energy, right? With each time it absorbs laser light, it gets some energy, but then it absorbs more energy than it got, or it emits more energy than it got. So the net effect is, with each time we absorb laser light, the atom is going to radiate away a little bit of energy. So if my atoms start to lose energy, what are they going to do? They're going to start to slow down. And if they slow down, they're going to get colder, right? Additionally, light can exert a force, right? It can push on things. And we're hitting the atoms with 6 different beams, sort of coming at them in all directions. So our laser light is sort of pushing and confining the atoms to kind of stay where they are right here, right? So the atoms are radiating energy away, and the light is sort of confining to keep them where they're at. So I kind of like to think of we've somehow confined the atoms in this sort of optical trap, right? I envision this in my head as the atoms are just stuck in a bowl, right? I mean, that's not literally what's happening, but the light is confining them to stay there. So it's like you're collecting atoms in a bowl, and they're stuck there, right? They're trapped from the light. So here's a picture of a setup of this. So if you look closely, there are 3 laser beams set up. We have this laser beam here, we have this laser beam here, and then there's one coming up here, right? This one's kind of hard to see. But those are your beams all coming together, right, on this chamber right here. So this now is in a vacuum chamber, right, because all this has to be done in a vacuum. And so in here, you have your atoms that are being sort of clumped together and confined with the laser light. So you're using sort of, you can think of light as exerting a pressure, right, that confines the atoms in a small space right here. And keep in mind, as they are absorbing that laser light, they are radiating energy away, okay? So this is laser cooling, right? We're using lasers to continuously remove and siphon energy away from the atoms, and in the process, confining them in this optical trap. And so we can see that here. So here's a real picture of some laser-cooled atoms. So this is an infrared camera, and we see this bright, ball here. This is about 800 million laser-cooled rubidium atoms, all sort of stuck in the middle here between all these laser beams. And the size of this, right, it's about ½ an inch, so use that as a scale to think about how big this ball of atoms is. And so here's the thing. The temperature of these atoms is incredibly cold. So this is about 100 microkelvin. So the lasers have cooled the atoms down to 0.0001 Kelvin. This is 100 millionths of a degree above absolute zero, right? This is really cold. And that's all because, again, the lasers, right, are causing the atoms to radiate away more energy than they absorb from the beams. So this is laser cooling. So that's with rubidium. This is with sodium. So sodium has a nice yellowy color, so you can see it with your eyes. So here's your vacuum chamber. And so behind this glass wall here is this clump of about 1 billion sodium atoms at 0.0003 Kelvin. So this is in a vacuum chamber, but realize what is on the other side of this window. The temperature of the atoms that we see here are about 1 million times colder than the air in this room, right? It is incredibly cold. And for this work, right, this was a very great experiment. So this ended up winning the 1997 Nobel Prize in Physics. So we've taken lasers and we've shined them on, atoms, and we've cooled them down to 300 microkelvin or 100 microkelvin, right? That's 1 million times colder than this room. So I think you'd agree we have really, really, really cold atoms. Could we make them even colder? Yes, we can. And in fact, everyone in this room knows exactly how to take these really, really cold atoms and make them even colder than this. So how can I make these colder? You do this every day. Let's say you have a cup of coffee and it's too hot. What do? Right? You blow on it. Right? You blow on it. What are you doing when you blow on it? Right? Well, you see this here. This is some evaporation. That's the hottest of the coffee atoms, right? Or molecules, whatever you want to call it, right? Coming up. And then you blow them away. Realize that you are selectively removing the hottest atoms from your coffee. What's left is cooler coffee, right? You're removing the hottest atoms. You're blowing away the hottest atoms. So this is called evaporative cooling, right? You're letting the hot coffee atoms evaporate, leaving a cooler coffee. What I want to do is basically the same thing, but with my laser-cooled atoms. So let's go back to here. Here are my atoms confined here, right? And the goal is the following. This is the idea. Let's take our laser-cooled atoms, which are at a balmy 0.0001 Kelvin, and let's blow on them, right? Like you blow on hot coffee or hot soup. That's going to remove the warmest of these really, really, really cold atoms. But what's going to be left is only the absolute coldest of the cold. Okay, so how are we going to blow on these atoms? Well, here's what we're going to do. Here is our sort of atoms in a bowl, right? This is our collection of laser-cooled atoms. And this is really cool. This is a picture of those atoms. So you can take a picture of them, right? If you flash lasers on really quickly before this thing dies, you can take a picture of what it looks like. So this is just, a cloud of atoms. And here's what we're going to do. I want to lower the walls of this bowl. Think about what that's going to do. If you have atoms that have enough energy to fly up the walls of this bowl, they're going to leave, right? They're going to fly over the top. So that's going to help selectively remove the hottest atoms in my bowl. And so when we do that, right, the cloud, we lose some atoms, but the cloud ends up becoming a little cooler because we're removing the hottest of those atoms. And we keep doing this, right? Lower it even more. So that means if you have atoms with enough energy, again, they're just going to fly out of my trap. And what's going to be left are the atoms that are so cold that they don't have enough energy to fly over the walls of this bowl. So what we're doing is we're effectively blowing on this like you blow on it with coffee. We're letting the hottest atoms evaporate away. What that does is that leaves only the coldest of the cold atoms left in, your trap. Okay, so this is where it's going to get really weird, because at these incredibly low temperatures, the physics of atoms behaves very differently. What happens are the quantum mechanical properties start to become important. And let me explain what I mean by that. When you have a gas, right, you model the atoms as just point particles, right? We can all imagine, these gas molecules here whizzing around. We can watch them move around. You can imagine you're a gas molecule bouncing off the walls. But when you make the atoms really, really, really cold, something very strange happens. These particles here stop behaving like particles and start behaving like waves, right? So instead of being a billiard ball particle here, this starts to behave like a wave, a little ripple. And we get this collection of atoms that are actually behaving like waves. And it's very challenging to explain why that happens, but that is what happens. And what's really neat is, as you keep lowering the temperature of your atoms here, these waves start to get longer. They spread out in space. They get longer and longer and longer as the atoms get colder and colder and colder. So basically, all of these waves get really long, and they're starting to completely overlap each other. And what's happening here is, I don't know what's happening here, right? I can't even tell where the atoms are, right? I just see wavy, squiggly lines, right? So all the atoms have basically started to become utterly indistinguishable from each other, right? The entire collection of atoms is combining as one big wave, right? These are all just waves that are adding together, right? So think of adding lots of ripples together. It turns into one big wave. So you get something like this. Now, it's very difficult to imagine what the atoms are doing here, right? Again, we can easily picture ourselves as a gas molecule flying around this room, but I have no way to conceive or to conceptualize what's going on in this third picture here, right? The atoms are completely indistinguishable from each other, and they're acting as just one big wave. So what the heck is this thing? Well, it's certainly not a solid, right? It's not a solid, and it's certainly not a liquid. Is this a gas? I mean, is this what gases do? No, it's not a gas either. This is actually yet another state of matter. This is not a solid, not a liquid, not a gas. It's a new state of matter, and it has a name as strange as its properties. This is called a Bose-Einstein condensate. And this is the most bizarre state of matter you can ever think of. So what I want to show you is an animation of this happening. Again, another really cool animation. We're going to start with a gas, and we're going to make it really cold, and we're going to watch it turn into, from lots of gas molecules, into this Bose-Einstein condensate. Okay, so here's our gas molecules, right? We can watch them. I know where they're at, right? This is just like the gas in this room. And what I want to do is start cooling it down. So when you cool down a gas, they start to move slower, right? the temperature starts to drop. But when they get really cold, they start to display wave-like properties. And as they keep getting colder, those waves get bigger and bigger and bigger, right? And they're starting to overlap. And so what's going to happen when all these waves are completely overlapped? Right? They turn into one big wave. And that's what's called a Bose-Einstein condensate. I have no idea where the atoms are there. They're all acting as one wave, right? This is the most bizarre state of matter imaginable. You can't possibly think, I know what's going on with the atoms there, right? It's just one big wave. And this happens when the atoms get utterly, inconceivably cold. Okay, so we can look at pictures of this happening in real life. So this was the very first time that a Bose-Einstein condensate was created. So what you're seeing here these are just atoms. So again, if you flash on lasers, you can take a very quick picture of this stuff before it dies. And this right here is 200 nanokelvin. So what we've done here is, right, we took our laser-cooled atoms and we allowed the hottest to evaporate away. Right, we blew on the coffee, and what's left is a clump of atoms that are 200 nanokelvin. That's billionths of a Kelvin. And then we keep evaporating more away. So this thing keeps getting colder. And all of a sudden, at around 100 nanokelvin, you see this big, bright white blob form, right? That's the Bose-Einstein condensate. And if we keep cooling even more by allowing even the warmest of these atoms to go away, you have something that's at half a nanokelvin. That's 0.5 billionths of a degree above absolute zero. And so this is that Bose-Einstein condensate. So what we have here is this collection of atoms. They're all overlapped as one big wave, right? You can't conceptualize what's actually happening here. But what we do know is that it's a collection of atoms at an inconceivably cold temperature. So this is made out of rubidium. We've now reached 0.5 nanokelvin. So look, that's a lot of zeros. And the average speed of the atoms, 0.3 millimeters per second. That is so slow, right? If the atoms were here when I started talking today and we're heading towards the door, they still would not be there yet, right? The atoms are moving incredibly slow. And this was a monumental result in physics, and so this was a slam dunk for the Nobel Prize. So this is a really cool video of this process occurring. So we'll play this a few times. But basically what you're seeing here is as we cool this thing down to, fractions of a degree above absolute zero, right, you basically are boiling away these warm atoms. And what's left, when this spike is here, this spike is basically telling you that all of the atoms are occupying the exact same place, right? That's because they're all overlapped in that big wave Bose-Einstein condensate. So you have all the atoms just sitting there, all acting alike in lockstep. They're all doing the same thing, and what they're really doing is they're at rest, or as close to rest as you can get, right? Because they're moving at 0.3 millimeters per second. To really understand how cold this is, I have this scale here. Let's call Omaha room temperature, and then let's call my nose, right here, 160 miles away, absolute zero. With that scale, the temperature of the Bose-Einstein condensate is about the width of your hair away from my nose. We are so incredibly close to absolute zero. And what's really cool is this Bose-Einstein condensate is the first time that you can actually see something that's purely quantum mechanics, purely quantum mechanical with your eyes, right? So we can see that with our own eyes. And so, right, slam dunk for the Nobel Prize. Okay, so the record currently right now for how cold we can make atoms, this was published in 2021. There was a group here from France and Germany. They were able to cool atoms to 38 picokelvin. So pico is trillionths. So this is 38 trillionths of a degree above absolute zero. So this is quite literally the coolest stuff in the universe. Thank you very much. Any questions? Oh, no, you could do it with any atoms. But some atoms it's easier to do than others. All right, well, thank you, everyone. Yes, question? This is a great question. So this is really cool, and actually we're trying to do this in Morrison Reeves right now. So there's a magnetic field that the bowl is actually made out of. So if we actually go back to this picture, I never mentioned what this was. These coils here, these are coils of wire, and we run current through them, and it makes a magnetic field. So I call this a magnetic bowl. So the atoms are kind of confined in this magnetic bowl. Very, very good question. Yes? So yeah, the question is, if it's so cold, how does it not condensate in the vacuum? Well, the vacuum, there's nothing in it, so there's actually nothing to cause that condensation, right? By definition, so you have to do all of this in a very, very, very good vacuum chamber, because if you have any kind of atoms that are moving around at all, and they strike this thing, I mean, it's just going to blow it to smithereens, because, right, we're talking about something that is nanokelvin, and the air in this room is, 1,000 miles per hour. So there's nothing in the vacuum chamber to do that. So we would have to remove like all the water, vapor, and stuff. So that's something you have to do to make sure that that happens. Yep. Yeah, so what we've done, one of the big results here, first is by improving the accuracy of the atomic clock. So imagine if your atoms are moving really slowly, I can now measure the frequency of that ticking longer, right? Because I can watch it longer because they're moving really slowly. So now that gives me more accurate clocks. And so now we have clocks that are accurate to 18 decimal places. And you might be thinking, okay, well, why do I need that kind of accuracy? Well, when you have satellites and stuff moving in space, right, we have to have time accurate to that level if we're going to send, beams of or radio waves or other light waves out in space and back. So it allows us, for one, to get better clocks. The other thing is, this is how people are studying the atom. And so, because now I actually can, hold my atoms right here. So there are a lot of people who are doing fundamental physics research, but the starting point is with these really cold clumps of atoms. Good question, thank you. Yes? Oh, like how you mean like stuff like this? This picture? That is an excellent question. So basically, here's what you do. You have your magnetic bowl that everything is in, right? And it's like, okay, I want to take a picture of this thing. So I drop it. And as it falls, I flash on another laser from the side, and the atoms absorb that. And I kind of look at where there is no light in my laser, because the light was absorbed by that thing. So it's kind of like an X-ray. It's the same idea as an X-ray. And so this is a false color image. So that's called absorption imaging. So I have to kill the thing to observe it, so destructive imaging. But that's how we do it. We drop it and take its picture by flashing on a laser really quickly, and it absorbs the light. Yes? Yeah, so let's go back to like when quantum mechanics started, right? You really could never actually see quantum mechanical things. This was the first time, this picture right here was the first time that we could actually see something purely quantum mechanical with our eyes. And so from there, we've been able to study the quantum behavior of atoms. So remember that picture I showed with the ripples, right? So that's claiming that atoms behave like waves. And so now, what if I would take like two of these things and collide them together, right? What happens when two waves overlap? They interfere. They make an interference pattern. And so that's actually what the next thing they did here. They took two of these and they basically, fired them at each other, and you could see this interference pattern that is only going to happen if you have wave-like properties. So what that did was confirm the wave-like nature of particles, which again was formulated way back in the 20s, but now you can actually see it, right, with your eyes. And so again, it's kind of just extending our knowledge by looking at the quantum mechanical behaviors of atoms. Yes? Oh yes, I was waiting for somebody to ask that, right? Can we get to absolute zero? Actually, we cannot get to absolute zero because there's some interesting things. If you've ever heard of the Heisenberg uncertainty principle, right? Atoms always are going to have some kind of minimum energy. And so there will always be a little bit of energy, even if it's ever so slight. And so that's going to prevent the atoms from ever truly being stationary. And we can never actually get to absolute zero. That's a great question. It will never happen. We can only get closer and closer and closer to it.
All right, thank you, Brad.